weather and climate often cause concern and curiosity, but understanding the facts behind the phenomena can be a challenge. We're here to help. From the University of Illinois, Urbana-Champaign, and Illinois Public Media, welcome to Weather Realness, a weekly podcast about the skies above Illinois and the world. From the University of Illinois, Urbana-Champaign, and Illinois Public Media, welcome back to Weather Realness, a weekly podcast about the science behind weather and climate in Illinois. I'm your host, Maddie Stover, a doctoral student in physics here at the U of I.
And I'm Steve Nesbitt, head of the Department of Climate, Meteorology, and Atmospheric Sciences at the University of Illinois, Urbana-Champaign.
Usually on this podcast, we're talking about the weather and climate here on Earth, but this week we're going much, much higher.
Yeah, we're talking about the first Illinois-led NASA mission.
We're talking about a satellite named after a pioneering African-American scientist.
And we're talking about a launch that will help study space weather.
5, 4, 3, 2, 1. Engines full power. And liftoff. Go Falcon, go IMAP, go SWIFO L1, and go Carruthers.
On September 24th, 2025, a SpaceX rocket blasted off from Cape Canaveral, Florida, delivering the Carruthers Geocorona Observatory to space.
Joining us in the studio a few days before launch is Laura Waldrop, the Electrical and Computer Engineering Associate Professor who is leading this mission. Welcome, Laura, and congratulations.
Thanks so much. I'm excited to be here.
So, Laura, what's going through your mind as the satellite prepares to launch?
Well, I admit I've waited on this moment for years now, and it's almost surreal. I'm very, very excited.
So, Laura, what is space weather? I'm a meteorologist, and of course all of us know what weather is, but what is space weather and why study it?
Well, so space weather describes the numerous effects on Earth caused by solar activity. A lot of people, I think, certainly when you look at the sun, it doesn't seem to be changing over time. But in fact, it is constantly emitting a steady stream of gas and magnetic fields that can impact the Earth. So the Earth has a protective magnetic bubble and typically shields out many of these effects. But sometimes the sun enters an active phase and can emit huge blobs of very, very energetic material that can have effects on Earth. So one of the most common, I think, that people are familiar with is the aurora in both the northern and southern hemispheres. This is a direct result of solar storms hitting the Earth. But other space weather effects include things like strong current systems that can be set up in the atmosphere. They can even couple to ground currents, which can impact power distribution grids. Then they regularly affect ground-to-space communication navigation networks.
So before we jump into talking about the mission itself, we'd love to know how you first got excited about studying space weather.
Oh, fantastic. Yeah, I got into it as an undergraduate, actually, at Boston University. I took a course with a professor who studied the exosphere, actually, and he did it through ground-based sensors, and these were looking at the glow that the exosphere gives off, but his sensors were looking at the visible emission, which means that you could only make these observations on really dark nights. And so what that meant was that when we would do a campaign, I joined his research group, when we would do a campaign, it was staying up all night. And I just thought that was so much fun. And it really sparked the interest for me that's carried me through my career.
So how will the Carruthers Geocorona Observatory provide new information about space weather?
Well, so the Carruthers Geocorona Observatory is really a revolutionary type of a mission. It's the first dedicated mission for exospheric science. So we've had many observations of the exosphere before, but they've never been the primary science goal of the sensor, for example. And so we just didn't have a lot of data. what the Carruthers Geocorona Observatory will do is take image after image where the only science we're interested in is the exosphere. So we've been able to design both the spacecraft and the scientific cameras themselves explicitly with that goal in mind.
And who is this observatory named after?
So Dr. George R. Carruthers, incidentally, was a 3-time University of Illinois alum. And with this being Illinois' first NASA mission, we're very excited to continue his legacy. But he was really a pioneer. He was a space physicist. He was an educator. He worked at the Naval Research Lab after he graduated from Illinois. And he invented the first camera that was able to take images of ultraviolet emission, ultraviolet light. So the human eye is not sensitive to ultraviolet light. If we could see the glow that the exosphere gives off in the ultraviolet, the night sky would not appear dark. And he invented the first camera that could do this. It was deployed by Apollo 16 astronauts on the moon. And in fact, that camera is still on the lunar surface today. What they brought home was the film canister, and it was the first image ever taken of this incredibly vast region around our Earth that emits this ultraviolet glow.
And can you give us some more perspective on the science that we get, like why we study why we would want to take those pictures in the ultraviolet?
Sure. So it's very difficult to make any other kind of measurements of this region. So this is Earth's uppermost atmospheric layer. It's truly vast. So it originates roughly near 500 kilometers altitude. This is where the vast majority of Earth's satellites orbit. It's known as low Earth orbit. But then it extends almost halfway to the moon. And even though it's very tenuous, so there's not a lot of atoms up there, as being the outermost atmospheric layer, of course, they taper off to zero as you go higher and higher, farther and farther away. But they interact with the other ambient particles in Earth's near-space environment in a way that controls the speed of recovery of Earth from these geomagnetic storms. So because we don't know very much about the density and the shape and even the size, we don't know how big the exosphere is truly. We've had such little data. And because it's so big, you can't just send a sensor up there and measure it directly because it's just too huge for that, So we take pictures of it from far away, and by looking at the glow that it's giving off, we then infer the density distribution of these particles that are emitting this light. And once we know those densities, we're now able to improve our ability to forecast things like geomagnetic storm recovery timescales.
And that recovery timescale correlates to impacts on our power grid or telecommunications?
Absolutely. So right now, in response to a solar storm, for example, many satellites actually turn off their electronics because they can be damaged. Airplanes divert their typical polar trajectories, the shortest path, right, cross intercontinental travel. They divert around the auroral zone because those currents can be damaging to passengers on the airplane. And so having a better understanding of how long a storm might last will help humans and their technological systems will be able to know how long do we need to be protecting ourselves, when can we go back to regular operation.
Back in May of 2024, people as far south as Florida were treated to a celestial light show as a geomagnetic storm set off in Aurora, which also caused some disruption to satellites. Here's an excerpt of coverage from NPR science correspondent Jeff Brumfield.
Yeah, so as I mentioned, it can disrupt communication with the satellites. It can also, the radiation itself can damage them. But the other big issue is the atmosphere can puff out, causing drag. And that's a big deal. Today there are close to 10,000 satellites in orbit, somewhere in that neighborhood. A huge chunk of those are satellites for Elon Musk's Starlink service. Now, Musk tweeted earlier today that these Starlink satellites are under a lot of pressure, though so far holding up. But, as this goes on and there's more drag on these satellites, all their orbits are going to change a little bit. The debris in space, its orbit will change a little bit. And so it's going to be chaotic up there.
For those just tuning in, you're listening to Weather Realness, the podcast about weather and climate. I'm Maddie Stover, a doctoral student in physics here at the U of I.
And I'm Steve Nesbitt, head of the Department of Climate, Meteorology, and Atmospheric Sciences at the University of Illinois Urbana-Champaign.
We're talking with Laura Waldrop, the Electrical and Computer Engineering Associate Professor who is leading the launch of the Carruthers Geocorona Observatory, a satellite that will orbit the sun and capture high-resolution ultraviolet images of the Earth's upper atmosphere.
So, Laura, these can be pretty long mission timelines in terms of the time from proposal to actual launch. Can you kind of take us through that process and how long it took, and in terms of things like constructing the actual satellite as well?
Sure. So the original solicitations, the way it works is that NASA releases a solicitation, says we have this launch in mind. We're going to be launching a truly, it's a very rare opportunity to go this far away as we need to be to take a picture of the entire exosphere, Geocorona, in one image. Those launches occur roughly every 10 to 20 years. So NASA released a solicitation that says we have a launch coming up. We're going to be actually deploying satellites into this particular orbit. And this is perfect for exospheric science. So the solicitation came out. The original proposals were due in late 2018. And then it's what's known as a multi-phase proposal process. Among all of the submissions, NASA chose 2 for further concept development. And we spent the better part of a year putting together a second proposal. That one was 1,006 pages, and it was submitted in 2020. And then we heard later that year that we had been selected for what's called implementation. So at that point, we started purchasing the hardware and building the components. This was very much a multi-institution effort. The University of California, Berkeley led the design and development of the ultraviolet cameras themselves. And Ball Aerospace, now known as BAE Systems, built the spacecraft bus, so all of the power and propulsion and the antennas so that we can talk to it. And then it went through a round of testing, and then all of the different subsystems were integrated. More testing, quite a lot of testing. And meanwhile, the team here at Illinois started writing what has turned out to be a massive amount of software needed to understand the data once it comes down. So that's very much an in-house effort. And now that we're launching, we'll have about 3 months in order to get to our Vantage, which is 1 million miles away from Earth. And once there, we'll have a minimum 2-year primary mission lifetime.
Well, so you'll be counting down the days to first light images coming back.
Absolutely. Oh, I couldn't be more excited. In fact, the days I'm counting down to are the opening of the doors. It's the only moving part on our spacecraft is when we pop open the doors on the 2 cameras. And I would very much like to be in the mission control room when that happens, because even though the only way you know it's been conducted successfully is a few numbers on a screen, the whoops and hollers are pretty exciting.
Yeah. Will you be able to be at mission control for that stage?
I intend to be. Our Missions Operations Center is also at Berkeley. They manage and operate, really, many of NASA missions. And so, yes, I'll be flying out there for that.
On September 24th, 2025, a SpaceX rocket blasted off from Cape Canaveral, Florida. delivering the Carruthers Geocorona Observatory to space. Illinois student newsroom reporter Adrian Reitz attended the launch party and filed this report.
More than 100 people sit in complete silence, looking up at the large screen at U of I's campus instructional facility. They've all risen early to witness this moment, live streamed from Kennedy Space Center. It's Uma Raharja's first time seeing a launch. She's a freshman in mechanical engineering.
You don't get these at all in Indonesia, where I come from, so...
The cheers at each milestone suggest it was worth getting up early to see. I'm Adrian Reitz, IPM News.
For those just tuning in, you're listening to Weather Realness, the podcast about weather and climate. I'm Maddie Stover, a doctoral student in physics here at the U of I.
And I'm Steve Nesbitt, head of the Department of Climate, Meteorology, and Atmospheric Sciences at the University of Illinois Urbana-Champaign.
We're talking with Laura Waldrop, the Electrical and Computer Engineering Associate Professor who is leading the launch of the Carruthers Geocorona Observatory, a satellite that will orbit the sun and capture high-resolution ultraviolet images of the Earth's upper atmosphere. What are you looking for? What are you planning to analyze it for?
Sure. So the way that we look at these images, or the way that we interpret these images, the first step in our image processing is calibration. So one of the advantages of having a dedicated exospheric mission, one of the benefits of that, is that we also control our calibration operations. We can point. We don't have to only stare back at Earth. We can point off of Earth and calibrate using stars, or we can actually measure the background emissions surrounding Earth and those things. So the first step we do is to calibrate the image using that calibration data. But once we understand then how much we've isolated now just the light that the exosphere is giving off, this ultraviolet light, what we're looking for is the distribution of the exospheric atoms, these hydrogen atoms that are emitting this light. So we're looking for how big is it? At what point does the light fall off into the background? That's going to tell us, that's going to give us a sense of the actual size of the exosphere. Does it extend halfway to the moon? Does it extend all the way to the moon? We don't know. Is it more elongated in the direction of the sun? Like if the sun is shining on it, we know that solar light can cause is essentially there's a form of pressure, and so you can think of it as a wind that's blowing. Does that mean that the exosphere shape has a tail in the anti-sunward direction? Again, we don't know, but that's something we'll be looking for. Another thing we'll be looking for is whether or not there's any spatial asymmetry. So, for example, we know that the way that hydrogen atoms even escape the lower atmosphere and populate this upper atmospheric region is very much controlled by temperature. And we know that it's typically colder at dawn than it is at sunset. And so we're very curious to see if to what extent is the exosphere asymmetric in that regard then? Are there dawn-dusk asymmetries? And so those are the kinds of things we'll be looking for.
How is the Carruthers Observatory going to make it to space? Is it using a NASA rocket, or is it using one of the private sector rockets?
It's using a SpaceX rocket, and when I say it's a rare launch, my understanding is this is the second time SpaceX has launched the Falcon 9 rocket. This is Falcon 9. It's launched many, many times, but this is what's known as its full thrust configuration because it's going so far away. So I mentioned earlier the ideal vantage for exospheric science is to get far enough away that the entire exosphere can be captured in just one picture, and that's 1 million miles away. We will be, this particular rocket is deploying 3 spacecraft on the same launch that will be essentially separated from that launch vehicle one at a time. But we're all 3 going to this same point in space, so to speak, or near it, which is a point in space where Earth's gravity balances the sun's gravity. So it's very easy to hang out there, so to speak. You don't need a lot of propulsion. You're not fighting against a lot of gravity there to try to stay on orbit. But because it's so far away, 1 million miles from Earth, you need a pretty big rocket to be able to deploy satellites that far.
So, Laura, what sort of missions to study space weather would you like to see in the future?
That's a great question. So I think one of the drawbacks of historical missions has been that because it's important to measure so many different aspects of space weather simultaneously, you need many different types of instruments. For example, the IMAP mission, which is the flagship mission for this launch, the Carruthers Geocorona Observatory is what's known as a rideshare secondary mission that's piggybacking on the launch. IMAP has 10 different instrument suites. And in order to measure many different aspects simultaneously of space weather, among other things. And many NASA missions are like that. They have many instruments that measure different aspects of space weather. And that's important. And they all go on one satellite. But what's really needed, in my opinion, and I'd like to see more of in the future, is constellation deployments of satellites, so that instead of measuring a lot of different parameters at one point in space from the one satellite, you're able to measure them over a more distributed area. And I think that's also true for ground-based sensing as well. That's been one of the limitations of our knowledge about space weather in the past, is that one of the ways we are what I like to call data starved is that we know what we need to measure. It's just a matter of measuring it at the spatial coverage and spatial resolution to really advance these forecasting models.
And that big spatial coverage is important in kind of understanding our response here on Earth to these electrical storms, how to protect our communications and power grid. Is that the motivation behind it?
That's very much a key motivation. Yes, absolutely. I mean, of course, there's fundamental science questions that we also want to know the answers to. But as far as practical human benefit, societal benefits, it's really unquestioned that will play a big role in advancing that knowledge.
So those of us that study weather and climate, since the Trump administration has taken over, we've seen a lot of big cuts to NASA Earth science. And I'm wondering, has that been the same on the space science side of the house?
It has, actually. Several missions, for example, that have been continuously operating, to everyone's surprise, for more than 2 decades have recently been cut without a technical reason why. It's a, again, political programmatic decision. And those kinds of cuts are particularly concerning to me because one of the benefits of having long-running missions in particular is that you can really start to see trends. A lot of people think that climate change is something that only happens at the surface of the Earth. But in fact, even in low Earth orbit, there are significant long-term changes occurring that have a lot of significance for operating space missions, satellite missions, including communication satellite networks and so on. When the atmospheric density slowly decays over time, it means that satellites live longer, which then has an effect on the population of space junk and collision avoidance, and there's a lot of trickle-down impacts of that. Not being able to monitor this environment continuously is a concern of mine, and so cutting missions like that is an unfortunate.
Also on the economic side, like these programs are such a huge investment of taxpayer dollars. Bill, you talked about, the years it took to build up this satellite and then to have it canceled. It seems like a kind of inefficient use of funds.
Absolutely. The story I like to tell that's the perfect example of that is Voyager. So, of course, Voyager is no longer conducting the science that it was designed to do. It did its flybys of the outer planets and took amazing data. But now it's entering the outer edge of our solar system, and it's entering a really unbelievably new environment that we really don't understand well at all. And the financial cost of maintaining communications with Voyager and continuing to receive the data from Voyager is so minuscule. But my understanding is that every year, or every review cycle, I should say, it's a real fight to keep Voyager funding going. We're talking about not even a few $1 million. In the scheme of things, it's pennies on the budget. And so, but these are conversations that are had continually, and it seems like such a shame.
Yeah, we're sort of entering unknown territory in our climate system as well, and our Earth orbiting satellites provide a lot of baseline about how the atmosphere has been changing. And so to bring it back home, of course, we have to know how the Earth is behaving in order to be able to predict how it's going to change in the future.
I completely agree. I think the critical thing here is data. Without data, the models can only be trusted so much.
So I want to kind of elaborate a little bit more on space trash, which you mentioned before. This is kind of old satellites or rocket stages that are no longer in use, that are in low Earth orbit. A recent study came out that showed this could be affecting our climate here on Earth. So just to give the listener some perspective, according to the United Nations Office for Outer Space Affairs, at the end of March 2025, there were around 15,000 individual satellites orbiting the Earth, and that number is rapidly increasing. And then once these satellites are no longer in use, they burn up in the atmosphere. So this creates a lot of space trash. NASA estimates that as of 2022, there were 9,000 tons of debris in Earth's orbit. That's about the weight of 9,000 pickup trucks worth of space trash. A recent study found that space trash burning in the atmosphere could impact our climate here on Earth. Steve, can you tell us a little bit more about this study?
Yeah, there were actually a couple studies that came out in the last couple of years, one by Ferreira et al., that was really the first to discuss the impact of burning up on re-entry of these satellites coming back into the upper atmosphere. And usually, that phrase is used by my kids to describe my sense of humor, burning up on re-entry. But in this case, it's not a joke, and it turns out that the aluminum that a lot of satellites are built with can break down on burnup and produce a lot of what we call aerosols, or tiny particles of aluminum in the upper atmosphere. And we kind of assumed that that was just going to be up there and not really affect anything. But it turns out that through chemistry and radiation processes, this could impact our ozone layer and cause the ozone hole repair that's happening over the southern hemisphere in particular to slow down. So, of course, that impacts people directly by potentially getting the harmful impacts of UV radiation at the surface. In addition, a further study by Maloney et al., who's at NOAA, described impacts on the upper atmospheric circulation. And through the aerosol radiative impacts of that aluminum oxide that forms following the reentry, it actually is affecting things like the polar vortex, things that impact our winter weather. Causes the polar vortex to become stronger, which causes our winters typically to be warmer. So this might be an interesting climate feedback that we need to study further to help understand the impacts of these satellites. Now, it may not seem like a big deal today, but we're launching a lot of these satellites, and some estimates are that we could have over 60,000 of these satellites by 2040, which would release thousands of tons of aluminum in the upper atmosphere. Yeah, certainly something we need to keep a watch on because obviously, we've probably all seen the movie WALL-E and what that looks like. But in addition to having all that trash up there, it might have impacts on our climate and people as well.
Mm-hmm. Yeah. Laura, do you have any thoughts on these studies?
I sure do. Space weather actually has an impact on this because space weather can change the upper atmospheric density and cause ripples in the density, so density waves, for example. And imagine a speedboat that encounters waves, strong waves, right? It starts to bounce up and down. These waves can cause satellites to change their trajectories. The density in the atmosphere is essentially a source of frictional drag on satellite trajectories. And when you change that amount of drag, especially when you impose perturbations and waves, so to speak, in that drag. Satellites, when they slow down, change their altitude, and it increases the risk of collisions, which can then increase the amount of space junk exponentially. And so, going back to having a better understanding of geomagnetic storm response at Earth and in this region of low Earth orbit, that can potentially help understand how many satellites will be re-entering during a potential storm. It happens all the time. More satellites drop out of orbit during geomagnetic storms. And having that then flow into this understanding, as you say, the teeny tiny particles, when you do have satellites or any other space junk deorbit, and as you say, burn up in the atmosphere, burning up just means big pieces turn into little pieces. And sometimes those little pieces, like the aluminum, can stick around for a very long time and change the upper atmospheric chemistry significantly.
So when you say that during one of these storms, these satellites can get knocked out of. Let me do this again. During these storms, satellites can get knocked out of low Earth orbit. Could they plummet down to Earth during that?
They absolutely can. In fact, it's happened before. So recently, Starlink launched, as they routinely do, dozens of communication satellites, for example. They bundle them on a given rocket launch and pop them off one at a time into low Earth orbit. And they launched right at the onset of a geomagnetic storm. This was less than a year ago. And I don't know the exact number. I think it was something like 30 immediately plummeted back to Earth because the density had increased so much more than they had forecast. They weren't prepared. They hadn't yet reached their target orbit before they encountered that enhancement in friction. As I understand it, the expected lifetime of these satellites is something like 10 years, which means that they're constantly planning replacements.
You're listening to Weather Realness, and we've been talking with Laura Waldrop, Electrical and Computer Engineering Associate Professor. She led the first NASA mission connected to the University of Illinois Urbana-Champaign, the deployment of the Carruthers Geocorona Observatory, a satellite that will capture high-resolution ultraviolet images of Earth's upper atmosphere. Coming up, we'll talk about when and where is the best time to see leaves change their color in Illinois. Stay with Weather Realness, the podcast about Illinois weather and climate.